Everybody. Welcome to another exciting afternoon with your host, me, Dr. White, and you'll be having fun with organic chemistry. I do. All right. Important thing I do want to mention. I don't think I haven't done it yet. Because of some legal considerations that were pointed out to me by the school, I'm going to be uploading a new signature form that I'll ask you to get back to me as soon as possible. The reason why I'm doing this is if I don't, then I really can't put things up on YouTube. And I know a lot of you are helped by YouTube, so that's why I'm doing this, lawyers. But anyways, please do that. And let's get started. Before we do that, I have an important question to ask you. Did you think about alkanes when you drove by a gas station? Did you think about alkanes if you use natural gas to cook with? Did you think about alkanes if you looked at baby oil or Vaseline or lit a candle or saw a candle? Boy, remember, organic chemistry is all around you. And it won't hurt if you think about it outside our Zoom lecture. So always feel free, and you should, think about organic chemistry in your daily life. It's there, and you're going to learn a lot more this semester. But please, next time you drive by a gas station, think about that gasoline has about half of it is alkanes, which you know what they are, which are saturated hydrocarbons. All right, let's get going. I'm going to be going through now chapter 2, the alkanes problem set. Now, please upload some answers next couple of days in the assignment area, D2L. Now, what I didn't have a chance to do, because yesterday I lost internet for a good part of the day, but I'll try and do it by Friday, is I will add to Blackboard, wrong school, D2L, don't tell the dean, I'll put up all the folder with the problem sets for the whole semester and with the answers to the problem set. When I made my course shell, I was told you can't do that. Well, this isn't a course shell, so I'll put it in. Another thing I do want to talk about is you people have been very nice to me so far. So guess what? Dr. White likes to be nice back. So Monday, take the day off. Don't come to Zoom, just take the day off. If you have any other classes at ECC, take the day off and tell them Dr. White said you could. By the way, it's Labor Day. There will be no classes. And because I spent extra time last Wednesday, and I'll do that today, we'll be caught up. But have a happy Labor Day in case I forget. Excuse me. All right. Now, when we go through the problem set, what I like to do is go through one page at a time. If you have any questions, ask. If I'm in sharing mode, which I am, it's better for you to use the microphone if you have one. If not, do chat. And if I miss someone, let me know I'm missing someone's question in chat. Because it's hard to see the chat when I'm in sharing mode. But we'll do one at a time. If you want me to do all of them, I can, but usually I'll pick one or two. If you have a question, if not, I'll pick one or two. All right, let's get going. Let me clear up the screen, which I should have done earlier. I'm assuming all of you can see Alkane's practice problem. Thank you. And now let's go through them. All right, these are all skills you should have for test number 1. First one, how many carbons are in the longest chain. If you notice, Dr. White was very nice. I didn't even put any hydrogens there to confuse you. And if we look at, and unfortunately, and I'm going to be working on this, converting these back to Word documents so I can write on it. But for now, you'll see my cursor. Let's look at C. How many carbons are in the longest chain? Go across this way, 5. Now, you could have counted 1, 2, 3, 4, or 1, 2, 3, 4. And don't forget, right now, you have to use your high level math skills for my class. Which number is greater, 4 or 5? And the answer is 5. Now, the longest chain doesn't have to be across. In organic chemistry, usually it is, but not always, especially on tests. Ooh, I shouldn't have said that. But anyways, 1, 2, 3, 4, 5, 6 this way. 1, 2, 3, 4, 5, 6. I see a question. I'll get to you right now. All right, Angela, remember, if your internet goes in and out, I will be posting all this on the video or in the video on YouTube by sometime later today. So that way you won't miss anything. And always feel free to come to my office hours too. Don't forget, oh, it's commercial from Dr. White. Don't forget, I have my office hours tonight from 6 to 7:30. I understand about your internet. Yesterday, I lost it all morning, which is rare. I think it's happened like 3 or 4 times like that in the last 8 or 9 years I've had WOW internet. And I had a class yesterday that obviously didn't happen. I let them know once I got internet happen, I'll make it up. All right, let's continue. Let's do one more. These are good. Ooh, let's do F. Now, F, if you count across 1, 2, 3, 4, 5, 6, that's one chain. Other chain is 1, 2, 3, 4. Remember, chain means carbons bond together. And 4, 5, 6, 7, 8, 9. There's one more chain I didn't mark here. I'll show you. 1, 2, 3, 4, 5, 6, 7, 8. So the longest chain is 9. Hopefully all agree 9 is greater than 6 or 8. All right. Now, when it comes to naming, first of all, you have to be able to do this. And an important skill you should have, hint, is give the IUPAC name for the following molecules. And hopefully you've learned the 2 tables I gave you, alkane names 1 through 10. By the way, IUPAC, I think, goes up to a couple 100,000, maybe a million. I don't know. I've never used that. But I do know the IUPAC names up to 20, even though after 12 you use common, not even after 10 you use common. I'll teach you later than IUPAC. But here, find the longest chain. If we look at B, 1, 2, 3, 4, 5, 6, and that's hexane. Here it's, whoops, no name. Now I showed it this way. I will not be using this until we get into fats and oils. And that's way later in the semester, like week 13 or 14, maybe even 15. I think 13 or 14. So don't worry about it. But this has 9 carbons, no name. Now, if we look at D and E, and remember, there's no such thing as a dumb question in my class. Always feel free to ask. All right. What's the longest chain? 4 this way, or you could have done 1, 2, 3, 4. Usually the longest chain, whichever way you count it, if you have 2 choices, gives the same name. This would be true in these 2 problems. But I wanted to illustrate a point. So this would be butane. These 4 carbons are spoken for. What do we have left? Oh, it's your friend, the methyl group. And what carbon is it on? You start from the carbons. That's always from the end counting. This way would be on carbon 2. If I started from this way, 1, 2, 3, 2 is smaller than 3. When you're naming which carbon something is on, you always use the smaller number. That's the IUPAC rule, and that's the one I'll follow when I grade. Now, I showed you E, which is the same name. You say, how can they be the same? I don't have it yet, but later today, I should be getting my package with my models, so I could have shown you this, but, oops, don't have my ring on. I'll have to, during the break, put it on. Hold on one second. I feel naked without it on. Success. By the way, I will not leave my house with this out, not on my finger. And over the last decade, I've gotten in the habit of putting it only one place if I take it off, so I know where to look. Because before that, I spent like 20 minutes looking for this because I wouldn't leave without it. That doesn't happen anymore. Anyways, back to what I was saying. If I said, oh, look, my left hand. And then I said, close your eyes. And you did. I said, open your eyes. They said, oh, look, something different. You said, no, you just rotated it 180 degrees. Well, it turns out molecules don't exist glued on a piece of paper. They rotate. And therefore, going from D to E, all I've done is rotated 180 degrees. All right. Does anybody have a favorite, F or G? Anybody have a favorite? Going once, twice? All right, let's do G. If I look at G, what's the longest chain? 1, 2, 3, 4, 5, 6, 7, 8, 9. I could go this way. 1, 2, 3, 4, 5, 6, 7, 8. Or I could go this way. 1, 2, 3, 4, 5, 6, or 5, 6. So 9 is the longest chain. No name. This is all spoken for. What's left over? A methyl group and 3 carbons to the center carbon is called an isopropyl group. And therefore, we have methyl and isopropyl. Now, remember, I'm not holding you to the alphabetical rule for an IUPAC, but I hold myself to it. So that's the answer I put down, but I'll explain another answer you could have put down in a second. What carbon is the methyl group on? 2. What carbon is the isopropyl? 4. If you started from this end, it would be 1, 2, 3, 4, 5, 6, 7, 8. So it'd be 6 and 8. And I think you'll agree 2 and 4 are smaller than 6 and 8. Now, if you didn't write this, if you had written 4 isopropyl, 2 methyl, no name, I would give you complete credit because that would be all right by me when I grade it, but this is the correct IUPAC way of doing that. All right, here we have a ring. Remember, every bend in a line is a carbon. You don't show hydrogens. And therefore, 6, that if this were a straight chain would be hexane. It's a ring. Don't forget cyclohexane, as I did, I think, last week once. Bad Dr. White. Everybody, listen carefully. On test number 1, common mistake, people don't put cyclo. I'm telling you that so you don't make that mistake. So whenever you're writing the name of a ring, make sure you use the prefix the part that goes in front of the IUPAC number name. Cyclo, remember, rings you designate by the prefix cyclo. Now, when there's only, and if I miss something you want me to do, always feel free to ask. If I look at this ring, 6, hexane, ring, cyclohexane. Oh, it's my favorite group again, the isopropyl group, and Dr. White loves T-butyl groups too. And 3 carbons, center carbon to the ring. When there's only one group substituent, in this case, the alkyl group on a ring, you use no number with a ring. Now, let's look at K. Now, K, first of all, you see the ring. 5 carbons, pentane, ring, cyclopentane. You have a T or tert-butyl and an ethyl group. Now, this one follows 2 IUPAC rules that I won't hold you to. One is, the first one, the group with the higher alphabetical priority, the one closer to the front of the alphabet, gets the lower number in a ring. And you ignore prefixes. So this is a B, this is an E, therefore the tert-butyl is 1. And you number clockwise or counterclockwise to give the other substituents, in this case the alkyl groups, the lowest number. So this is 2. So the correct IUPAC would be 1 tert-butyl, 2 ethyl, cyclopentane. Remember, cyclo, ring, pentane, 5 carbons. However, on a test, there are 3 other answers. Yes, 3 I would accept. If you have these numbers switch, that would be all right. You said 2 tert-butyl, 1 ethyl. If you had the 2 ethyl first and the 1 tert-butyl second, I would accept that. If you have the ethyl first, tert-butyl second, and the number switch, I would accept that. Don't tell the IUPAC, please, I'm being nice to you. Shh. All right, now, there are 2 skills, and I got my numbering mixed up, I see, that you should have when you talk about nomenclature of organic molecules, in this case, the alkanes and the cycloalkanes. Remember, nomenclature is a fancy word for name. And that other skill is draw the condensed structure, and that means you don't have to show every carbon-hydrogen bond for the following IUPAC molecules. And here you'll know you've learned the name. Now, I didn't put lines here because this was small. If you do or don't, I don't care. For these, when you're writing the structures, remember, there are 4 bonds to carbon. 4, yes, 4. 4 bonds to carbon. And that's your friend on test number 1, 2, 3, and 4, and the final. Remember, there's always 4 bonds to carbon when you're putting your hydrogens or drawing any structure. And if we look at that, and if we look here, hexane, 6 carbons. And how do I know there are 3 hydrogens there? 1 bond to carbon, 4 minus 1, 3, and so on. Now, let's look at F. How do you know what to decode? You start from the right and move left. Start from the right, move left. Hexane, 6 carbons. Also, I found when I'm drawing structures, I leave the hydrogens for last. That makes your life easier. Methyl, CH3. Di means 2, tri means 3. So there are 2 methyl groups. Uh-oh, the dash fell off from between the 3 and D. Don't tell anybody. But anyways, and we're each of those 2 methyl groups on carbon 2 and 3. Now you can call this 1, 2, and 3, or you could have started here. This is 1, put the methyl groups on this side. Either way, it's correct. You're just rotating the molecule. Now let's do some rings. Here I made a mistake number-wise and order-wise. Don't tell anybody. I didn't correct. I was too lazy. But anyways, here we have cyclobutane. Butane, 4 carbons, cyclo a ring. You call that a square? No, organic chemists call it a ring. Now, if we look here, how do we decode this? Start here, cyclopentane, pentane, 5 carbons, cyclo ring. One of the carbons has T-butyl or tert-butyl. Right here, doesn't matter which carbon, most of you are going to put it up here, but Dr. White felt like messing your brain up a little, so I put it over here. And then carbon 2, that would be my ethyl group over here. But let me just do it like this. Most of you would probably do it this way. Ran out of room on the top here. This is 1, this would be 2. And that's the way most of you probably drew it, but there are other ways and they're all the same. All you're doing is rotating the ring. All right, on to test, and you'll see this as we get further into semester. I'll talk about more today. A skill you should have, and it's an important one in organic chemistry, is give the reaction products for the following. And if we look at the first one, we have propane plus oxygen. And what does it give? CO2 and water. Now, what I didn't do, and I'll do right now to remind you, how do you approach one of these problems? And here you have to give the product or products for the following reaction. How do you do that? You look at this, and hopefully you've learned the general reactions that I'm giving you now. This is an alkane, but it could have been a cycloalkane, which it's not. You react it with oxygen, you need a spark here, which I don't put down. And what do you get? The actual chemicals, carbon dioxide and water, or if you want, you could have put the water first and the CO2 second. Therefore, alkane, what are you going to get? CO2 plus water. And this is a general reaction that for test 1, you should know, meaning memorize. Now, some of my best students always put this general reaction underneath their answers on a test. Some of my best students never do, but all my students who do well in my class have learned these and memorized these general reactions. If you notice, if we look at C and B, this is an alkane, oxygen, gives CO2 and water. This is a cycloalkane, oxygen, gives CO2 and water. So all these can do the same when you do combustion. Now, quick thing about your everyday life. Unfortunately, in a few months, it's going to get super cold around here. And if you remember when, like last winter or other winters, you're out driving either yourself or with someone, and you see the car in front of you, and you look at the tailpipe, and there's liquid coming out of there. And you say, oh, that's gasoline. That car is going to catch on fire. No, that's not gasoline. What happened is that person probably just started their car, driving around, and the whole muffler assembly and exhaust system is still very cold. And the hot water vapor, water is a gas, which you can't see, goes into the exhaust system, is condensed, converted back into a liquid, and that's what you're seeing falling out of the tailpipe, water. Why? Because in the car engine, when it's running properly, combustion happens. Alkanes, remember gas station, from the gasoline combust to give carbon dioxide and water. And you're not going to see carbon dioxide, but you will see the water. All right. Any questions concerning the problem set? Going once, twice, let's move on. All right. On Monday, I showed you your first general reaction, hydrogenation. And hydrogenation is where you take any double bond. Remember, R is just like an X and Y in math. That means anything with carbons and hydrogens in it, and other atoms too. Same thing here, and all this is a way of saying a double bond. And whenever you have a double bond and reacting with hydrogen, a catalyst, and a catalyst is something that makes a reaction go faster. And for this one, you use platinum, palladium, or nickel catalyst. They're different types. Dr. White has done this reaction both in a lab and in a chemical plant, supervised it. And what happens is you break the pi bond of the double bond, and each carbon gets a hydrogen. Remember, double bond is something you should know, has one pi bond and one sigma bond. You break pi bonds real easy. You never break a sigma bond, which is why this is here. And I started showing you how to do chemical reactions. Remember, you don't have to balance it. If I were to ask you 3 points each, hint, and for these type of products, problems, hint, or questions, I would ask, give the organic product or products for, and let's say this was A. What do you do? From here on out, every time you look at an organic molecule, you should look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Oh, look, a double bond. And immediately in my brain, and hopefully in yours too, this comes up, double bond. What am I reacting with? Hydrogen. What do we have here? A catalyst. And a catalyst can be platinum, which we are using, or it could be palladium or nickel. And what happens? You break the pi bond, and each atom of the double bond gets a hydrogen. Do you break carbon-carbon single bonds? I got to do this. No, you never break carbon-carbon single bonds, or rarely, only in combustion. In my class, other than combustion, you don't. So therefore, you have 1, 2, 3, 4, 5 carbons, and they're connected together by sigma bonds. So I'm going to end up with 1, 2, 3, 4, 5. These 2 carbons are the double bond. I've lost the pi bond, as you can see right there. I didn't write it. These 2 carbons, what happens? My general reaction says each one gets a hydrogen. And now I know there are 4 bonds to carbon. Now, you could have written this carbon and this one as CH2. You can, but you don't have to. This is less work for you, writing it the way I have. And that's how you do hydrogenation. And it's time for you to have some fun, because Dr. White's been hogging all the fun. Your turn. What would be, oops, what would be the organic product or products for the following? Have some fun. And when you're done, give me a thumbs up. And remember, I try and give everybody time to finish. Like I said, when you're done, give me a thumbs up or smile or both. All right, I think everybody's done. If not, scream at me. Nope, I don't hear anybody screaming at me. All right, let's take a look at this. How do you do it? You look at the molecule and you look for what's different. What's not a carbon-carbon single bond or carbon hydrogen? Oh, look, double bond. What am I reacting it with? I'm reacting it with, and this is pretty ugly looking H2, but that's better, hydrogen and a catalyst. Therefore, I know, hint, you know, and something you should be working on, hydrogen and a catalyst, where the catalyst can be platinum, palladium, or nickel. You break the pi bond, and each carbon of the double bond gets a hydrogen. Remember, double bond is 1 pi bond and 1 sigma bond. Do you break carbon-carbon single bonds? No. So I have 5 carbons here. I better end up with 5 carbons. And you don't change the position where they are. Which carbons had the double bond? These 2. Notice I've broken the pi bond. There's only 1 line there, not 2. And each carbon, you can, since I've got something underneath, you can put this one on top or bottom. I like to put it on bottom. Am I done? No, there are 4 bonds to carbon. 1, 2, 3, 4. I'm done there. This has one more because one hydrogen plus these. Oops, made a mistake. Nope, I'm right. And finally, the last one, 4 minus 1 is the 3. And this is how you do it. Now, there's something I need to show you. And the question would be, give the organic product or products are the following. And you look at this and say, oh, a ring. No, a ring is just carbon-carbon single bonds and hydrogen. Same thing, a methyl group. Oh, what do we have here? A double bond. Remember, there's a carbon here and a carbon here, and that's 2 lines between it. So I know, and you will be learning, hopefully you know, hydrogen and a catalyst. The catalyst can be platinum, palladium, or nickel. In this case, we're using nickel. You break the pi bond, and each carbon of the hydrogen of the double bond gets a hydrogen. Remember, double bond, 1 pi bond, 1 sigma bond. By the way, each line is a pair of electrons, or each bond. I tend to forget to mention that, but we're dealing with electrons. So, first of all, do you break carbon-carbon single bonds? No. Therefore, I still have my ring, I still have my methyl group. Now, these were the 2 carbons of double bond. Notice I broke the pi bond. There's no 2 lines there. Am I done? Yes. Why? Because you don't show hydrogens on a ring. Let's take a look at this carbon over here. And if we count it, 1, 2, 3. So if I had shown it, which I'm doing it red because I won't normally, be 1 hydrogen, same thing here. Now, you do not have to put this on a ring, but I'm going to show you. How many bonds does carbon? 1, 2. 4 minus 2 is 2. Same thing here. So we've gone from 1 to 2. Yes, we have added our hydrogen. Look out, I'm having a good ring drawing day. And it's your turn. What would be the product or products for the following chemical reaction? Organic product or products. Hold on, let me get to whoever had a question. Now, Barb had a very good question, and let me answer it. Let me get back to that. All right, what I write underneath here, the general reaction. Do you have to write that down in a test? No, but I do when I do my classes, because this helps you, I'm actually helping you memorize it. And in my brain, this fires off. When I see this, this comes up. It's in the back part of my brain. I think it's stored. And this happens, and this also happens. Do you have to write this down? No. If you just want to put cat there for your own benefit while taking a test, you can. If you don't want to write any of this down there on a test, you don't have to. And hopefully that helps. I was just trying something. It seems to make a noise every time I do that. All right. Anybody need, if you're done, give me a thumbs up. Hopefully your thumb works today. That was a bad joke. Remind me never to use that again. Ah, that was awful. All right, let's do it. When you look at an organic molecule, look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen, you should get your attention like that. And, ooh, a ring, nope, carbon-carbon single bond, but oh, look, a double bond. And if I look, I'm reacting with hydrogen and catalyst, and the general reaction is carbon-carbon double bond, reacting with hydrogen and a catalyst, and the catalyst can be platinum, palladium, or nickel. And if we look at this, we say double bond, you break the pi bond. Remember, double bond has one pi bond. No, you don't have to write this down in the test, but this is something you should have in between your ears, in your brain. And you break the pi bond, and each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No, never, except for combustion in my class. Therefore, we have our ring. The T-butyl group is still on the ring where it was. The methyl group is on the ring. I'm going to put in my hydrogens because I know there are 4 bonds to carbon. And if you notice, I did not draw the double bond here because it's gone and I'm done. On a ring, you don't have to show hydrogens. And notice this one had 1, it's now got 2. Remember, 4 bonds to carbon. And that's how you do hydrogenation. All right, a couple of interesting things. First of all, later, how many of you have ever heard of hydrogenated fats and oils? Plus, they're not healthy for you. Well, you have a double bond of fats and oils, and I'll teach you later, and you add hydrogen, you break it. And that makes those fats and oils less healthy for you, but more profitable, I'll teach you later on, for certain companies, which is why they do it. The other thing is, time for a little Dr. White story. When I first started in industry, my first project was hydrogenation. I'll teach you later on, not of this double bond, but something else, and used one of those catalysts. And I was brand new, right from academics, and I didn't know any better. And I learned real quick about costs of things, and that is platinum and palladium is about, back then, $100 a pound. Nickel catalyst is about $2 or less a pound. So when you're calculating how much does that reaction cost, if you use platinum and palladium, it's going to cost you a whole lot more. And I went to my boss, because I was brand new, and said, all right, I'm going to be working on this. I'm going to use these conditions and this catalyst. And he looked at me and says, do you really know the price of platinum, palladium, and nickel catalyst? I don't think you do. Go look it up and come back to me. And I did. And I came back and I said, platinum and palladium aren't used around here, are they? He said, no, nope, nope, too expensive. And I learned my lesson. And that was my first boss. Dr. McDaniel was great. He taught me a lot. Unfortunately, about a year and a half later, he left the company. And because of things I did, I was given his job as section head, which I was the youngest section head ever in Axel at that time. All right, it's time to move on to the next reaction. And the next reaction I want to teach you is called halogenation. Now, there's something I need to talk about, and that is this right here. When in organic chemistry, X means the halogens fluorine, chlorine, bromine, or iodine. And whenever you see X, that's a lousy X, that's a better X, organic chemists are talking about fluorine, chlorine, bromine, or iodine. And if you don't know, I will teach you now, halogen gas, fluorine, chlorine, bromine, or iodine exists as a diatomic gas, such as chlorine gas is really Cl2. So let's look at this new reaction called halogenation. This is any double bond reacting with a halogen. And notice up above, I show you, in this case, X is fluorine, chlorine, bromine, or iodine. You break the pi bond. Remember, there's one pi bond and one sigma bond. And each carbon of the double bond gets a halogen. So again, you have a double bond reacting with halogen gas. You don't need a catalyst here. Hydrogenation, if you didn't have a catalyst, you could wait days and nothing happened. With a catalyst, it's done in a couple minutes, or not that, halogenation really 4 hours. This reaction is almost instantaneous, and I won't go into the bond energy reasons why it's so fast, but it is. So you don't need a catalyst. So let's take a look at this. If we look at this reaction, the question would be, give the organic product or products for the following. What do? You look at the molecule and say, what's different? What's not a carbon-carbon single bond, carbon-hydrogen? Immediately, hopefully, it's sticking out like a sore thumb. That's not good. Like red and blue lights on a fire engine. It's a double bond. What am I reacting it with? Fluorine gas. And that's a halogen. Remember, the halogens can be fluorine, chlorine, bromine, or iodine. Do you have to write this underneath? No, but I will. You break the pi bond, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3 carbons. Here's my double bond. I've broken it. Here are my 2 carbons. Each one gets a fluorine. Fluorine counts as 1 bond. Therefore, this carbon has 1, 2, 4 minus 2, 1 more hydrogen. This has 3, 4 minus 3, 1 hydrogen. This has 1, 4 minus 1, 3 hydrogen. And that's how you do it. Let me rewrite it over here so it looks nicer, because I squished it in. And that's the answer. And if I look at my clock, it's time to take a break. I'll see you in 5 minutes at 1:55 because I'm going to go stretch because I have to. Sorry about being a minute late. I just got an order in from Amazon. I took it in. I didn't see any rubber gloves that I normally put on, so I had to stop and wash my hands. By the way, whenever I get my mail or any orders, I either put on rubber gloves or I wash my hands 20 seconds. Dr. White practices good, how should I call this, hygiene for the virus. Should be safe, but I'm not going to gamble. All right, we're talking about double bonds, and we're talking about halogenation, how you react the double bond with a halogen gas. Remember, X is fluorine, chlorine, bromine, or iodine. And here, what do? You break the pi bond, and each carbon of the double bond gets a halogen. So I better share the fun, and it's your turn. And the question would be, give the organic product or products for the following reaction and have fun. Because I was a minute late, I'll go an extra 5 hours. No, I won't. When you're done, look up and smile, or give me a thumbs up, or do something to let me know you're done. In classroom, it's easier. I just look around and see when everybody's done. All right, I think everybody's done. So let's do this. Question is, how do you determine what's the organic product or products for this reaction? And the first thing you should do, look at the organic molecules you're dealing with. What's different? What's not a carbon-carbon single bond or a carbon and hydrogen bond? And if you look right here, a double bond. And what are we reacting with? Bromine gas. So double bond, how do we show a halogen gas? X2, remember X can be fluorine, chlorine, bromine, or that's an R, or iodine. And double bond, one pi bond, one sigma bond. You can break pi bonds like that. And each carbon gets a halogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 carbons. I better end up with 4 carbons. Now, this is very important. Which 2 carbons are the carbons of the double bond? These 2. And our general reaction shows us that those 2 get the halogen, in this case bromine. If you put it elsewhere, it's wrong. And now I know there are 4 bonds to carbon. Let's look at this carbon right here. 1, 2, 3. Bromine is counting as a bond. 4 minus 3 means there's one hydrogen. Same thing here, here. And that's your answer. All right, let's do some more of these. They're fun. Let's look at this one. I'll do this one, then I'll let you have fun too. I share. What's different? Double bond. What are we reacting with? Chlorine gas, halogen. Double bond. Halogen. X can be fluorine, chlorine, bromine, or iodine. What happens? You break the pi bond, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bond? No. Therefore, I'm still going to have my ring. Now, it's important to realize my double bond carbons were here, which are here. And what does my general reaction show me? Each one gets a halogen. And what's the halogen? Chlorine. And that's how you do it. And it's your turn now. What would be the organic product or products for the following reaction? Don't forget, when you're done, give me a thumbs up. Or if your video's on, smile. Excuse me. By the way, I did it into my elbow, my arm. Oh, wait, I should have my mask. Wait, we don't have to in Zoom. All right, anyone need more time? All right, let's do it. Now, first of all, let me point out, this is a chemistry instructor's favorite trick on a test. I gave you a big, scary molecule. No, not if you know what to look for, it's not scary. What do you look for? Anything that's not carbon or hydrogen, and anything that's not a carbon-carbon single bond. And we have a ring, but that's just carbon-carbon single bond. Oh, look, we have a double bond. And you know, double bond, what am I reacting with? Iodine, I2 is a halogen gas, and therefore X, remember, can be fluorine, chlorine, bromine, or iodine. And you break the pi bond. Remember, this is one pi bond and one sigma bond. And each carbon of the double bond gets a halogen, in this case, iodine. Do you break carbon-carbon single bonds? No. So I'm going to have my six-membered ring. I'm going to have my methyl group. I'm going to have my ethyl group. Where are my two carbons double bond? These two. I break the pi bond, these two. My general reaction tells me those two carbons get an iodine. Now, if you have your iodine and methyl group switch, that's okay for this class. Don't worry about it. And that's how you do halogenation. I got a secret for you. You're doing organic chemistry, and hopefully it's not too painful. See, organic chemistry isn't that bad. It's fun, but I'm an organic chemist, so I'm very biased. Oh, I would invite you to, I'm not going to do it now. If you go to YouTube, by the way, don't forget I'm posting all our lectures or Zoom meetings on YouTube, and I try and do it the same day. It's a long upload because they're big files. But if you go to YouTube and you put halogenation of a double bond, you'll see some neat videos, and I'll show you next week. No, the week after when we do a lab, I'll show you about it. And if you take, say, bromine, which is red, and have a test tube with a double bond in there, an alkene, you drip it in there, instead of going red, it immediately reacts to form a clear compound, the halogenated compound. And I'll teach you that's an important test. But you should look at the video because it's so quick. It's actually quicker than I can do that. Ooh, it's working today too. I got my batteries in my hand. All right, let's continue on. Now, so far, if you look at what I've taught you, here in hydrogenation, you're adding a hydrogen to each carbon of the double bond. Here in halogenation, you're adding a halogen to each carbon, the same halogen of each carbon of the double bond. And this is called symmetrical addition, the same to both carbons of double bond. What happens if you're adding something different? Now, do not, and this is for unsymmetrical addition to a double bond, because if you have something like this, and if we were to call this carbon 1 and 2, in real life it'd be more complex. Does A always go to 1 and B to 2? Or could it be both? Or could it be B goes to 1 and A goes to 2? Well, it turns out this is very important in chemistry, organic chemistry. And a famous Russian organic chemist solved that question. And that chemist's name is Markovnikov. I'll never ask you who Markovnikov is, and do not write this rule down. I'll explain why. When Markovnikov's rule is stated one way, when an unsymmetrical molecule to form HA or HQ adds to an unsymmetrical alkene double bond, the hydrogen from HA or HQ becomes bonded to the unsaturated carbon atom that already has the most hydrogens. And you look at that and you say, what? What does that mean? Relax, take a deep breath, and I'll show you. Let's look at an example. That's the reaction, addition of an acid, HX, and here X usually is not all the halogens. In organic chemistry in real life, it's chlorine, bromine, or iodine. Hydrofluoric acid is one of the most dangerous chemicals to work, and you stay clear of that. But anyways, if you have a double bond and you add to that, and I'll write it on top here. You can write it like this or on top, HX, one carbon gets to H, the other gets to X, and it follows Markovnikov's rule. Years ago, I used to write out Markovnikov's rule, his name, and spell it wrong, which is not polite, because we honor his great achievement by using his name, and I just abbreviated M's rule. Now, let's look at it in real life. And here we're reacting this molecule with HCl. Look at the molecule and see what's different. What's not a carbon-carbon single bond or carbon-hydrogen. And you look there, a double bond. And we're reacting with HCl, and hopefully you'll be learning this weekend the general reaction, double bond, HX, X can be chlorine, bromine, or iodine. You break the pi bond, one carbon gets H and the other gets X, and it follows M's rule, Markovnikov's rule. Well, how do we do this? First of all, do you break carbon-carbon single bonds? No. So I'll do 1, 2, 3. Remember, these are the 2 carbons of the double bond. And now you got to do some high level, oops, I made a mistake. Somebody should have caught me. Shame on me, shame on you. Remember, it's your job to make sure I don't make a mistake with hydrogens. That's your solemn responsibility in my class. Now, how do you use Markovnikov's rule? You look at the 2 hydrogens on the 2 carbon of the double bond, this one and this one. How many hydrogens here? 1. How many hydrogens here? 2. Now you have to use your high-level math skill, which is a smaller number. Time's up. Hopefully you pick 1. Markovnikov's rule is the carbon of the double bond with the lower number of hydrogens gets the hydrogen. That's this one right here. So the hydrogen goes there. And now the other one, oops, wrong. I got it backwards. Dr. White's having a brain freeze today. Markovnikov's rule is the carbon with the most hydrogens. With the most hydrogens gets the hydrogen. In this case, 2 is greater than 1. The hydrogen goes here, and the halogen goes here. In this case, chlorine, and you fill in the hydrogens. Let's do another one so Dr. White can redeem himself for making a mistake. I'll do this one, I'll share. Let me get it right. and look at the molecule, what's different, what's not a carbon-carbon single bond, or a double bond, or carbon and hydrogen. And therefore, we have a double bond reacting with hydrogen bromide. Remember, halogens are shown in organic chemistry with an X. This can be chlorine for this reaction, bromine, or iodine. I think it might work with fluorine, but I've never seen it done. And I'll never put that on a test either. You have my promise. You break the pi bond, one carbon gets H, the other gets X, and follows M's rule. The carbon with the most hydrogens of the double bond gets the hydrogen. The other carbon gets the halogen. If you notice, this has 2 hydrogens. This carbon has 0 hydrogens, which is the larger number. Hopefully I'll pick 2. Do you break carbon-carbon single bonds? No. I have these carbons. Were my 2 carbons double bond? These 2. This carbon gets the hydrogen. This carbon gets the halogen, in this case bromine. Put in my hydrogens. And that's how you do it. Now, let me tell you something, I'll show you, and that's why I forgot to mention it, remind myself. Now, I can still remember when I was a sophomore taking organic chemistry for chem majors, and my instructor taught us Markovnikov's rule and said the best way to remember it is the following, and that is the rich get richer and the poor get poorer. And he said, if you don't want to remember that, you can remember this, and he apologized for his bad grammar. Them that has it gets it. And what do we mean by the rich get richer and the rich get richer, or them that has it gets it? In this case, we're talking about hydrogens. The carbon double bond with the most hydrogens, the richer one gets the hydrogen coming in. Or them that has it, the most hydrogens, gets it, this hydrogen. And that's how you do Markovnikov's rule, which is very important in organic chemistry. So I better let you have one to try. And why don't you try the following? What would be the organic product or products for the following reaction? Go. And this weekend, if you're at a Labor Day party, virtual or with your family where it's safe, you can show them Markovnikov's rule. People don't want to hear about Markovnikov's rule at a Labor Day picnic. Trust me, don't. All right, when you're done, give me a thumbs up. All right, I think everybody's done. Time to do this. Let's have fun with organic chemistry. Look at a molecule. Look what's not a carbon single bond or carbon or hydrogen, and we see right there double bond. I'm reacting with hydrogen iodine, double bond. Remember, halogens are abbreviated by X. In this reaction, X is chlorine, bromine, or iodine. And no, you don't have to write this under reactions. I always will. And you break the pi bond. One carbon gets H, the other gets X, and it follows Markovnikov's rule. And Markovnikov's rule is the rich get richer, the poor get poorer. And the carbon with the most hydrogens of the double bond gets the hydrogen coming in from the HX. Now you got to use your high-level math skills. This carbon has 2, this has 1, which is the greater number, and time's up. 2, the hydrogen will go to this carbon, the halogen will go to this one. Do you break carbon-carbon single bonds? No. Let me just minimize something on my screen so I can write this out. So I have 4 carbons. Here are my 2 carbons of double bond. This one gets the hydrogen because they had the most hydrogen to begin with. This gets the halogen, in this case iodine. I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. Remember, it's your solemn responsibility. Dr. White makes a mistake, you're to correct me. Oh, that was fun. Let's do another one. And here's some more fun for you to have. Give the organic product or products for the following. I should point out, these reactions allow us to make new molecules, which are used to make other new molecules for things you use in your daily life, or it's used to make those actual molecules which we use and you could use in your daily life. Don't forget to upload next couple of days your answer for some of your answers from problem set Alkanes so you can get your 1 point. All right, looks like everybody's done, but maybe not. If you're done, give me a thumbs up. All right, I guess I was right. Let's take a look at this molecule. And again, you're going to hear me say this throughout the whole semester over and over again, but it's something I do every time I look at a molecule. I immediately look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. And immediately I say double bond. And I'm reacting it with HCl. Halogens are shown as X. And now, and that can be chlorine, bromine, or iodine for this reaction. You break the pi bond. Remember, there's 1 pi bond, 1 sigma bond. Break the pi bond. Each carbon gets something. 1 carbon gets the hydrogen, the other gets the halogen. It follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon gets the halogen. The rich get richer, the poor get poorer. And if we look here, this has 2 hydrogens on there. This one has none, 0. Which is the larger number? Hopefully you pick 2. Do you break carbon-carbon single bonds? No. So I have 4 carbons across, and then I have these methyl groups. Now, here are my 2 carbons of the double bond, these 2. The first carbon, which has 2 hydrogens, will get my hydrogen. The other carbon will get the chlorine. I put in my 2 more hydrogens and I'm done. Now, this was the chemistry instructor's favorite trick on a test. I gave you this big, scary molecule, but the key thing is you are learning, look for what's different. The rest just comes along for the ride, which is what happens here. Now, I need to talk about something in organic chemistry, and that is Mother Nature and Dr. White love rings. Students don't. They don't like rings at all. Again, Mother Nature and Dr. White loves rings, but students don't. What do you mean by that? Well, let's look. And I'll do this one. Question B, what's the organic product or product for the following reaction? And if you look on screen, you'll see, ooh, this molecule, what's different? What's not a carbon? Uh-oh, my cloud thing just made some noise. Sorry about that. I have Adobe Cloud through my other school, which is good because it gives me video editing software. Every once in a while, it updates, tells me there are updates available. Anyways, what's different? There's a double bond. And therefore, I look here, double bond. That's a funky looking double bond. That's better. Double bond, HX. X can be chlorine, bromine, or iodine. What happens? You break the pi bond, one carbon gets H, the other gets X. It follows Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen, the other carbon gets the halogen. And we look here and say, uh-oh, I don't see any hydrogens. What do I do? Remember, there are 4 bonds to carbon. Everyone, 4 bonds to carbon. 4 bonds to carbon. And therefore, if we go over and look at this problem, what you have to do is look at each carbon of the double bond, this one and this one. If we look at this, there's 1, 2, 3 bonds, 4 minus 3, there's 1 hydrogen there. If we look at this carbon right here, there's 1 to the methyl group 2 plus my double bond, 2 more is 4. 4 minus 4, oh, that's 0. So let me fix up. Well, Dr. White's having a bad number day. No, I'm just kidding. So which is the larger number? 0 or 1? Time's up. Hopefully you pick 1. Do you break carbon-carbon single bonds? No. So I'm going to have my ring, still going to have the methyl group. Now, the hydrogen will go to this carbon right here, but you don't show it. The halogen will go to this carbon, and that's the product you get. And that's why students don't like rings. Dr. White loves them. So remember, when you have a ring and you're dealing with Markovnikov's rule, you actually have to figure out how many hydrogens are in there. And you count the bonds. Remember, there's 4 bonds. 4 minus number of lines or bonds to carbon tells you how many hydrogen. 3 lines, 4 minus 3, 1 hydrogen on there. 4 lines, 1, 2 plus 2 for a double bond, 0. And therefore, you have no hydrogens. And that's why the hydrogen goes to this carbon and the halogen goes there. Your turn. And why don't you try this one? What would be the product or products for the following reaction? And remember, whenever you have a question, ask, because in my class, there's no such thing as a dumb question. Take your time. And when you're done, give me a thumbs up. All right, I think everybody's done. How do we do this? How do you determine what's the product or products? You look at the molecule that you're reacting, you say what's different, what's not a carbon-carbon single bond or carbon or hydrogen. Oh, look, a double bond. And we're reacting with HBr, double bond, HX, remember X is used for the halogen. This reaction is chlorine, bromine, or iodine. And you break the pi bond. One carbon gets H, the other gets the halogen X. How do you know which? It follows Markovnikov's rule. The carbon with the most hydrogens in the double bond gets the hydrogen, the other one gets the halogen. Oh, it's a ring. How many? I don't see any hydrogen. No, you count. This one has 1, 2, 3. 4 minus 3, it has 1 hydrogen. This one has 1, 2, 3, 4, and therefore 4 minus 4 is 0. which is the larger number, and time's up. Hopefully all picked one. Do you break carbon-carbon single bonds? No. So I have my ring. And if your rings don't look as pretty or they look better than mine, that's even better, but we still have our methyl group. We still have our ethyl group, CH2, CH3. This carbon right here will get the hydrogen. The other carbon here will get the halogen. In this case, it's bromine. And that's the answer. Now, if you put the bromine over here and switched it so it looked like this, that's correct too. You can do it either way. Works for me. And that's how you do reacting a double bond with an acid, sometimes called hydrohalogenation, but just reacting with an acid HX. And it's important because a lot of times when you put a bromine or halogen on there this way, you can make molecules that have a certain structure or use this to, I'll teach you later on, as a building block to make other complex molecules. All right, let's continue on. Now, another unsymmetrical addition to a double bond is called sometimes, oh, I see a question. Hold on while I get to you. Barb, when you said, did I write the same thing twice? I think I got notification. No. When you say on top, I'm going to hold my cursor over this molecule. Which one do you call on top? Tell me in the chat. This one, this one, this one, this one, this one, this one went too fast. You mean right over here? Like here? Let me write it. Is that the one you were talking about? Barb? All right, this unfortunately is wrong, and I'd mark it wrong on a test. How do you know that? Let's go back, and that's a great question, because now you won't get this wrong on the test, which also makes me happy. All right, we're talking about Markovnikov's rule, or this reaction. The only carbons that you consider are the ones in the double bond. Therefore, the only carbons that will be involved in the reaction are the ones in the double bond, which is what our general reaction. And those are these two. This one is not involved, and therefore it will never get the halogen or hydrogen. And it turns out knowing where different things are going is extremely important, because this molecule, let's call it, I don't know, C, is much different than these, which are really the same, which I'll call A. If you make, this is a whole different molecule than these. These all I've done is rotate the molecule 180 degrees. There's no way you can rotate C. So it's a very excellent question you asked. And that is where you put the reagents is very critical. And just like on a math test, if I ask 2 + 2 is what, and you put down 4, that's the correct answer. If you put down 5, well, that's not the correct answer. Hopefully I got that right. I think I did. My first grade teacher would be happy with me now. Well, I got it right back then too. In organic chemistry, where you put atoms is critical because you don't get certain molecules like the one you're describing. All right, let's look at the addition of water to an alkene, also called hydration, of a double bond. And let me go through the general reaction. You have a double bond and react it with H plus. Now, H plus means any acid. In organic chemistry, usually you're talking about H2SO4 or other acids, which I won't teach you, like methane sulfonic acid or benzene sulfonic acid, not hydrochloric acid, because we just did this. Now, water, how do you think of water? Well, think of it as H and OH. OH, you'll learn later on, or even today, is called the hydroxyl group. If I can spell correctly. And we'll learn that when we get into alcohols more. So just like HX, think of water as H and OH. You break the pi bond, one carbon gets the H, the other gets the OH, and it follows Markovnikov's rule. And that's hydration of a double bond or addition of water to a double bond. Now, if I look at the clock, it's almost time for a break, but I'm going to bet we're done for today. And I'll say goodbye. Have a great Labor Day weekend and gehen gesund.